Hey physics students, Mr. R again, talking about the last topic in chapter 8, and that is fluids in motion. We're in a closed system. These fluids are showing laminar flow because the flow is consistent. Now there was a bit of a problem with my printer, and there are some lines here I want you to disregard. But as you can see, that this hyperbolic flow, this is consistent with laminar flow, because as you can imagine, there's friction. There's friction between the walls of this closed system and the fluid as it drags along the wall. So these vectors are going to be slightly smaller than the ones in the middle, where there's less friction. But there's going to be friction within the closed system, within the fluids, and that's an issue of viscosity that we won't take up now. But with the mechanics of fluids that we're going to talk about, we're going to assume that there's laminar flow, and laminar flow is just smooth flow, and we're going to disregard friction. The reason is because within a closed system we want the energy to be conserved, and so we don't want to have to address energy going to friction. Now this is the antithesis, this is the opposite, so to speak, of laminar flow. This would be turbulent flow. Turbulent flow, as you can see, is irregular flow, and you would see irregular flow frequently if there's an obstruction, and where this is addressed frequently is within the closed circulatory system, and because turbulent flow is going to result in clotting, and clotting then means blockage, and that's a problem. So turbulent flow, as you can see, is irregular flow. Alright, so laminar flow is smooth flow, and turbulent flow, as you can see, is irregular flow. Now, one term that is frequently used for this irregular flow are eddy currents, and you see eddy currents just beyond an obstruction quite frequently. So, anyway, ideal fluids are those fluids that are non-viscous, steady, meaning that it's not pulsating like the heart. The heart would result in pulsating blood flow. It's consistent blood flow. It's steady blood flow, and it's non-turbulent. And probably be best to describe that as laminar. So we're going to be assuming that we're dealing with ideal fluids, all right? And those are the ideal fluids. Those are the characteristics of ideal fluids. One of the things that we find in a closed system is that if the diameter narrows, all right, so what I'm measuring here is D. If the diameter narrows, and here's another D. We'll call this D1, and we'll call this D2. See how it narrowed? What do you think happens to velocity? Well, as the velocity increases, the speed will increase, because what we find is that the energy inside is always conserved. It always stays the same. So it'll slow where there's a greater amount of area, and it'll speed up. This vector is supposed to be longer than these vectors, illustrating that it's speeding up because it's much narrower. Because these fluids cannot be compressed, so you're going to have steady flow, and in order to get this steady flow, we're going to have to speed it up in the more narrow regions in order to get the same volume through. Right? So if the diameter narrows, in a closed system, velocity increases. I mean, we know that we've seen this. I mean, this is the whole idea of a dam and damming up a river. I mean, if it's not a closed system, it'll flood the neighboring villages. I mean, but we're assuming that it's in a closed system, right? Okay, so from this we get what's called the continuity equation. Assuming that it's an ideal fluid and assuming that it's closed. It's a closed system. And that's area 1, and we're going to get that from the diameter, so we'll call this area 1 times velocity 1, and we get velocity from our vector, so velocity 1 equals area 2, we get this from the diameter, multiplied by velocity 2. And that's called our continuity equation. Alright? So you find high velocity, low area, low velocity, high area. All right, inverse relationship there, right? Okay. Now, Bernoulli wants to point out, while we're on the topic of fluids in a closed system, Bernoulli wants to point something out before we get into equations. Bernoulli points out that the pressure in the fluid decreases as the fluid velocity increases. Right. This is a very, very important principle that Bernoulli came up with. And if we could measure it, we would use this device. This is glassware that's been carefully designed just to illustrate this point. This is a closed system. Imagine that this is a pipe, and I've just cut it so that we could see. You could see that it's a pipe. And this is open here, this is open here, and it doesn't really matter the direction of the fluid, but here we have the flow, and of course, because it's more narrow, the vector would be slightly longer, right? And if we put some fluid in here, what we would find is that it would not stay consistent because there's a pressure difference caused by the flowing water, right? This pressure would be low because the velocity is fast. This pressure would be high because the velocity is low. And so as you can see, we have a pressure difference there, don't we? All right. So that's an important Bernoulli principle that I want to point out. It's the reason why airfoil works and our airplanes fly is because as the air goes over it, there's less pressure, and the less pressure allows for lift. Because remember, air could be a fluid as well. So Bernoulli principle is important, and we use Bernoulli principle to in the lab to create a vacuum whenever we're in chemistry. We use Bernoulli principle to create a vacuum so that we can vacuum a precipitate. Perhaps you remember doing that with what's called a Buchner funnel. All right, that's very, very common. All right, let's get cracking on some problems. First, as a reminder that the volume per unit time is flow rate. All right, constant throughout a closed system. Right? And the flow rate is meters cubed per second. and that equals areas, and that's meters squared, times velocity, and that's meters per second. All right, so as you can imagine, you multiply meters by meters, you have meters cubed, and the all right, so we divide by seconds. So let's try the first one. Gas pipe, diameter 2.5, delivers 1.33 meters cubed of gas per second. What is the speed of the gas? Well, we should look at this, and first we should see that we're going to have to turn the diameters into area. So that's our first problem. And so we're going to have to say pi r squared, and so we're going to have to take half of this diameter, aren't we? Half of this diameter is 0.125 squared times pi, and that equals 0.05, and that's going to be an area, so it's going to have to be meters squared. So that's the first thing we have to do. Now that we have our area, let me just go ahead and say equals area. And so what we're going to say is flow rate 1.55 meters cubed equals 0.05 times velocity, and we want veloc. That's what we want, right? So that's simple enough. All we have to do to get velocity by itself is to take 155 divided by 0.05, and that equals 35 meters per second. All right? Now, then let's try another one. A 2 centimeter diameter faucet fills a 2.5 times 10 to the negative 2 meter cubed container in 30 seconds. What is the speed of the fluid as it leaves the faucet? Well, as you can see, we still have this problem of diameter and not area, and we also have this for 30 seconds instead of 1 second. So there's a couple of issues that I want to sort out first. So let's take the 2.5 times 10 to the negative 2 meters cubed divided by 30 seconds and turn that into and just divide that so that we can get how much it is for 1 second. That would be 8.3 times 10 to the negative 4th meters cubed. All I did was divide that so I can get this per second. All right, per 30 seconds is a bit confusing for me. And then I got to get, and then now I have to get the area again, right? And so the area is half of this. Well, we're going to have to turn that into meters here too, because everything else is in meters. So we're probably getting used to this. I'm just looking at it and just automatically thinking to myself, centimeters isn't working. I'm not showing you how to convert it into meters. I'm just quickly converting it here. All right, so here's our area. Lovely. All right, so we have so just like the last equation, we have flow rate equals area times velocity, and we want velocity again, so we're going to have to divide just like we did last time. Remember, flow rate equals area times velocity, and we wanted velocity. So here's our flow rate, and here's our area, and we want velocity. So 8.3 times 10 to the negative 4th meters cubed per second divided by 0.03 meters per second, and then we're going to lose a meter, aren't we? We're going to lose 2 meters, and we'll just get down to meters per second, so our units drop out very nicely for us. And when we divide that, it's 2.7 meters per second is our velocity. All right.